So that is the thing. So why do we now study chemical bonding? We study chemical bonding because there are some elements they want to be stable. We study it for stability. So the reasons for bonding is stability. If this is your first time in my class, this is not a class where we give much notes because we don't really have much time and we have much things to do. So I counted it the last time. We have chemical bonding, we have air, we have water, we have acid, base, and salt, we have oxidation and reduction, we have chemical kinetics, we have chemical equilibrium, we have thermochemistry, we have electrolysis. So there are still a lot of topics to do. Aside that, now you have inorganic and you still have the organic chemistry. So if we keep giving notes, if you want me to calm down and teach you chemical bonding, I might take like 2 weeks for every class because I will start explaining and breaking it down one after the other and giving you notes. But there's no time for that now. So you have to be smart. I will just be telling you all the important points you need. So pick them as I'm saying them and practice questions. Is that taking? Because there are a lot of things we need to do. But if you want us to be very slow, it will be at your disadvantage. We won't cover anything and you might not do well in the exam. So please, it's not everything that they need to spell out to you. 16 years. So why do we study chemical bonding, or why do elements go into bonding? They go into bonding because of what? Stability. And if they are to go into bonding, how do they do it? How do they go into bonding to attain stability? They do that using their valence electrons. Valence electrons. So they can ask you that when elements go into bonding, what do they use? They use their valence electron. Now, what are valence electrons? They are the electrons in the outermost shell of an atom. Abi, all these are what we have talked about on atomic structure, blah, blah, blah. But I'm still going to talk about it again. So now, if these elements want to attain stability, who are they copying? Why do they want to attain stability? There are some elements called the noble gases. These elements do not undergo reactivity. So every other element wants to be like the noble gases. And you remember the noble gases for simplicity. We have helium, we have neon, we have argon, and so on. Now, let me use helium and neon for example. I told you something in the last class, that when you have a configuration like this, 1, 2, 3, I told you something about this, that this configuration is very, very stable, Abi, because all the orbitals are filled. This one is not stable because it needs just one electron. And due to repulsion, then it will look for where to get the electron. This one is partially stable, but not also stable. But this is the one that is most stable. So anytime your orbital is completely filled, such orbital is said to be what? Stable. So if I'm arranging this now, then I'm going to say that C is more stable or stabler, as you can have it, than A and than B. Abi? So C is more stable. Now, let's look at the configuration of this guy. Helium, the atomic number for helium is 2, Abi? And that means it is 1s2. If you draw it in the shell, it's going to be this, right? So it's stable. Look at neon. The atomic number for neon is what? 10, Abi? So if you write that, that's going to be 1s2, 2s2, 2p6. So when you check the shell, it is completely stable. Can you see that? If you do for argon too, you will see the same trend. Now, when we did atomic structure, I told you about the quantum numbers. I said whenever this quantum number and these guys are the same, what do? You add these two together, Abi? So if you look at this, I can still write the configuration for neon as 2,8. Do you agree? Now, looking at all of this shell, everything is completely filled, right? So any element that has a completely filled orbital, completely filled orbital or shell is said to be what? Stable. Do you get that? It's said to be stable. But every other element on the periodic table do not have this completely filled orbital, so they are unstable. Now, these elements that are unstable, other elements, let's check them out. I have sodium, for example. Sodium has atomic number of 11. Configuration is 1s2, 2s2, 2p6, 3s1. Abi? So when you look at the outermost shell, there's just one electron, meaning that this shell will be needing one electron. But it does not stop there. That's why you have to understand those quantum numbers. There is still 3p, right? So in this S now, there's one electron. In the P, there is nothing. And for this guy to be stable, all of these guys must be filled. Better still, sodium will now do something. Let's reduce it to this. All I want is to look like neon. Those are the questions they will ask you. All I want is to look like neon. Then what do? I have to find a way to get rid of this guy. This guy is known as the valence electron. Abi? So let me find a way to get rid of this guy. And by getting rid of this guy, where will I throw it? It can't just be thrown in the atmosphere. Something must accept it. And that's why this other guy will call me chlorine. Chlorine atomic number is 17. Its own configuration is 2,8, 7. For this one that is 2,8, 1, it will need 7 to be 8. Abi? So it can do something. It can either lose 1 or gain 7. This one can either gain 1 or lose 7. Abi? Now, from what we did on periodic table, which one has the lowest ionization energy between the two of them? You see why I said you might have problems if you did not study what we did in the last class. Between sodium and chlorine, which one has the lowest ionization energy? Sodium. Because this electron in the outermost shell of sodium can be easily removed. For you to remove 7, you will spend more energy. And this one will now prefer to lose that one. Why this one will not want to lose 7? Because you are going to spend energy. But you can easily add 1 to this guy so that it becomes what? 8. But you can't easily add 7 to this. Meaning that chlorine and sodium will now look at each other and wink at each other. Hey dear, can I get 1 electron from you? Who is asking that question? Chlorine. Sodium, well, for I to be stable too, you can have it. Both of them will now come together and give birth to a child called sodium chloride. And why? When you look at it now, this one would have been Na+, this one would have been Cl-. Now, being Na+, you know what that means. That's 2,8. It means it has lost 1 electron. Being Cl- means that is what? 2,8,8. That means it has gained 1 electron. Now, if you now look at this configuration that sodium now attains, who does it look like? It's looking like neon. That means that sodium wants to be like neon. Chlorine wants to be like who? Argon. That's the basics of bonding. Do you get the point? Yes. But now, we might not be drawing all this magical transfer of electrons for time's sake. I might just break it down to you now. You have seen the basics, you have seen the introduction. The questions they can now ask you is, what type of bond is present here? So if I bring carbon and nitrogen together, they can ask you what type of bond is present. They can ask a lot of questions on this simple thing I just said here. The one that transferred is electron. How many electrons did it transfer? They can ask you. How many electrons did this one accept? They can ask you. What is the valence electron for this? They can ask you. What is the valency? They can ask you. The valency can either be 1 or 7. But which one will it prefer? It will prefer 1. All of those things are questions they can ask you. They can ask you to write the formula. At the end of the day, you look at the valency, then you write the formula. The valency is, what did this one accept? 1. So that means valency for chlorine is 1, but the valence electron is 7. The electron they use in bonding is what we call the valency. So you will understand them step by step. So now, let's go back to pictorial overview. So I said chemical bonding talks about the different types of forces that is present in atoms and molecules. And why do elements go into bonding? Because they want to attain stability. In order to attain that stability, what do they use? They use their valence electrons. Is that taken? So now, I want to rub these stories. Can I? So now, element is said to be stable if they have two types of configuration. The first one is called a duplet configuration. So when element has a duplet configuration, it is stable. Duplet means it is having just two electrons, and that example is helium. So helium is stable because it only has one s2, and the one s, you know, there is no 2m, 1p. So this one is stable. It has just two. Some elements you want to be like this guy, you will see. Then it is stable when it also has octets. Octets means it has 8 electrons. Let me put it here. 8 electrons in the outermost shell, 2 electrons in the outermost shell. Is that taken? I've shown you that from the picture. Element that has 8 outside, they are stable. Some elements that have 2, they are also stable. When they have 8 outside, they are said to be octets. When they have 2, they are said to be what? Duplets. So examples are your neon, argon, xenon, krypton, and the likes. All those noble gases. Noble gases. So now, leaving that reasons, when you are now talking about bonding, we have some terms you use. What are the terms we use? Quickly, there's what we call the valence electron. The word valence electron is talking about the total number of electrons in the outermost shell. That's valence electron. Electrons in the outermost shell. I hope you are following. So the total number of electrons in the outermost shell is what we call what? Valence electron. Then, what do we call valency? Valency is defined as the combining power of an element. So valency is defined as the combining power of an element. I will show you the difference between everything. Oxidation number. Oxidation number is just an indication of the electron loss or gain by an element or by an atom or by a group of atoms, which we call radicals. So, indication of the electron loss or gain is what we call oxidation number. Now, in the last class, we talked about group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. If I ask you, for group 1, what is their valence electron? All of them have 1 electron outside. Abi? That's what determines their group. How many does this one have outside? This one have... Do you understand that? So most of those elements, that's what they have in the outermost shell. I don't need to start drawing examples. You are not YX students. And you had A in chemistry. Abi? Now, valency. If an element is in group 1, the configuration might be 2,8,1. That's sodium, Abi. This is 2,8,8,1. This is potassium. This is sodium. Look at this guy from the stories I said at the beginning. If this guy wants to go into bonding, what do you think it will need to go into bonding? What will he have to do? Lose 1 electron. Abi, it means that 1 electron is what it will use for bonding. I hope you are following. So if I now say that what is the valency for sodium, it is going to be 1. It can lose 1 and it can also accept 7. Abi, but I'm going to do something. Do you think sodium will ever want to accept 7? It all depends on the condition. But the one it will want to use is 1. So we'll circle that. Do you get that? So now, that means that the combining power for sodium can be 1 and 7. I hope you are getting my point clear. Let's look at group 2. What do you think the combining power for group 2 can now be? 2 and 6. Do you agree? Yes. Out of the 2 and 6, which one do you think group 2 will majorly use? 2, because it's easier for them to lose 2 than accept 6. I hope you're following. For group 3, what do you think can be their combining power? They can decide to use 3 and 5, but which one do you think they will prefer? 3. 3 will determine their stability. That's why you can see Al3 plus. You don't see Al5 minus. You most times see Al3 plus. You know Al is in group 3, aluminium. So if you understand the basics that we have done before, this is 2,8,3, Abby. So it will prefer to lose 3 than to gain 5. That's what we are saying. Do you get the point clear? Group 4, they can either lose 4 or gain 4. Right? This one can either lose 5 or gain 2. Or gain 3. For this one now, do you think they will prefer to lose 5? Let me draw an example. Nitrogen. Nitrogen is 2,5, Abby. What does it need to complete 8? 3. You know it can have 2 and it can have 8. So if it's going to have 8, that means it will need 3 more. If it's going to be 2, it will lose 5. So will it now prefer to lose 5 or gain 2 or gain 3? Gain 3. So that means it will prefer to gain 3. This one will prefer to lose 3. So get it clear. So let's say the ones on this side are the lose, gain. Share you get. So this one will prefer to lose 1 than gain 7. This one will prefer to lose 2 than gain 6. This one will prefer to lose 3 than gain 5. This one will prefer to either lose 4 or gain 4. It's still okay. This one will prefer to lose 5. We prefer to gain 3 than lose 5. Then for this now, we gain 6. Oxygen is an example. What's the atomic number for oxygen? 8. So oxygen is 2,6, Abby. What will it prefer to do? Gain 2. So if they ask you for the combining power, that is 2. That's why when they give you a question, there's a way you can always write the formula. So I'll show you how you write the formula soon. Now, this one can either lose 7 or gain 1. But this one is already 8, so it will not lose nor gain anything. Do you get my point? So that's why the group 8 elements are called the noble gases, because their own configuration is complete already. So they don't need to lose neither gain. And how many times do you see people write sodium chloride, aluminium trichloride, and all of those things? You don't see them write neon chloride or neon something. You don't usually see these group 8 elements in formulas. So let's go back. Now, oxidation state quickly. If you indicate the electron you have lost, you know we said something. This one will either lose 1, Abby, so they will usually form plus 1. This one will usually form what? Plus 2, Abby. This one will usually form plus 3. This one can either form plus 4 or minus 4. Why this one usually form minus 3? Do you get that? This one will usually form minus 2. This one usually form minus 1. And this one will not form anything. I hope you are following. All this were still based on our knowledge of atomic structure and periodicity. So if you don't know how I've gotten the configuration, then that means you're just starting chemistry. So now that we understand these terms, I will now be talking about valency and using it to draw bonds. You should be able to follow me through. So can I rub the board now? Oh yeah, let's be fast. So please note that there is difference between valency and valence electron. The total number of electrons in the outermost shell is the valence electron. The one they will use in forming bond is what we call the valency. So I've been waiting for you. Are you true? Are you true? So now, on a broad type, there are 2 types of chemical bonding. So we now want to see how they are forming it now. This one that is losing 1, what will it do? In a case it might think about it that let me share this electron instead of giving it out. In another case, it will think about it that, oh, let me just give it out. Now, giving it out depends on who it is linking with. So that's what we want to see now. Can I go on now? Can I rub this board? So let's talk about the types of bonding on a broad basis. So we have what we call interatomic bonding. Interatomic bonding. From the word interatomic, it exists, it is a type of bond that exists between atoms. Between atoms. When you join one atom to another atom, then we call it interatomic. Is that taken? Interatomic. Then we have what we call intermolecular forces. And you could have guessed where that comes from. When you join molecules together, for now we might not spend energy on this. You talk about it in organic chemistry, but I will introduce you to it. So when you're talking about interatomic bonding, time wo mo máa ń bẹ̀rẹ̀ class gan, kí ló ṣẹlẹ̀? 6 minutes more. So between atoms, this exists between molecules. Wọ́n máa ń rán ọmọ ẹ̀ sí mi ni. Kò ní lé other teachers. So for interatomic bonding, it's good because if she does not always tell me, I'm allowed 2 hours. So from what we have here, please listen. I hope you are following my stories. Now, for interatomic bonding, we already said it. It's just like I'm having sodium and chlorine. So when I join sodium and chlorine together, it is called interatomic. When I join carbon and hydrogen, nitrogen and hydrogen. So if I'm joining atoms together, we call it interatomic. But I can have water joined to another water. That is called intermolecular. So I'm taking water and joining water to another water. It is called intermolecular. So I can join even as little as hydrogen is. Hydrogen gas and another hydrogen gas. I can join HCl and another HCl. So all this one, they are called intermolecular, and they have a lot of things to help us with. But in order to understand intermolecular, you have to understand interatomic deeply. So most importantly, solve questions. So now when you're talking about interatomic, if I want to join sodium and chlorine, there's a way I have to go. Let me give an example. Sodium 2,8,1, Abi. Chlorine 2,8,7. Please, if you look at this now, chlorine only needs 1. Sodium wants to give out the 1. So they don't even want to share. So sodium will transfer. That is what makes the difference. Sodium will dash it out totally. It will not share. But if let's say hydrogen and chlorine, look at the problem here. Hydrogen has 1. Chlorine has 2,8,7. How many does hydrogen need to complete? 1. Just 1. You remember it can have 2 or 8, Abi? So that's why there's another type of bonding. So here now, hydrogen needs 1, chlorine needs 1. Then the question is, who will give 1? Then both of them will now say, oh, let us reach consensus before police will come. Let us share what we have. My one, I will bring it closer to you. Your one, you bring it closer to me. So we'll be living like family. So anytime police come, I will show you I have a partner. And that partner is this. You give me your one, I give you my one. That means when police come, where's your two? This is it, 1, 2. Oh, you are complete. Where's your two? This is it, 1, 2. So both of them will now be scamming us. Do you get it? At the end of the day, they are sharing it. So in this case now, it will not be transferred. It will be shared. And that's why we have different types. And all of these things now determine properties and a whole lot of things. So let's start from the first one. So the ones that involve transfer, we call it ionic bonding. So there's ionic, or that is also called electrovalent. So let's look at the different ways they can ask you questions on this. Anytime you see a metal that is linking with a non-metal, when they ask you, just know that that is most likely ionic. When you see, they told you that, oh, take sodium and chlorine, for example. They now say, what type of bond is present? Sodium is what? A metal. Abi? Chlorine is what? A non-metal. Just know that's ionic. Do you understand that? So whenever you see a metal joined to a non-metal, that is ionic bonding. Whenever you see that it involves transfer of electron, that is ionic. How do we know? Sodium will eventually transfer its electron, Abi? It will transfer its electron to chlorine. We can't be drawing the shell. This is not WAEC. So we are going to now have Na plus, Abi, 2,8 plus Cl minus 2,8,7. So that's an example. So when it involves transfer of electron, that is also what? Ionic. All these are things you need to know. I was testing you. That shows you are following. So 2,8,8, not 2,8,7. Then the next one, when there is high electronegativity difference. So if they ask you that what type of bond will be present between elements of high electronegativity difference, it is ionic. And how do we know? You did periodicity. Chlorine is in which group? Sodium is in which group? So look at group 1 and group 7. You remember when we were talking about periodicity, we said electronegativity increase across the period. Abi? That means elements in group 7, we have high electronegativity. Elements in group 1, we have low electronegativity. So the difference, so if this one is having like 20, the next one might be having like 18. This one might be having like 16, like 14, like 12, like 10, like whatever it is, 8. So if I say 20 minus 8, you see that the difference is wide. But if I say 10 minus 8, the difference is less. So the difference between these two guys will be very high. So chlorine is in that position of high electronegativity. Sodium is in that position of low electronegativity. So anytime you notice that the electronegativity difference is wide, then that means it is what? Ionic. I hope you are following. You can only understand this concept if you understand periodicity. The next thing is that this element, there will be high polarity. High polarity. All these are conditions. You are a Jambite. You are not a WAEC student. You have to understand what you are doing, especially if you want to do well. You must express yourself. When you look at something, you know what it is saying. It's not about what your teacher said. It's about you knowing that, oh, they will say, Egbewa, bring it. That's what you will say. So when they bring it, you look at it and you analyze it and you tell them the answer. It's as simple as that. So now, this guy that we now formed, this is where the name now comes from. So when we form this guy, there's a property they now exhibits. So you now call it properties of ionic bonding. Properties of ionic bonding. Now, how did we form this? We formed it by transfer of electron. Which element does it involve? It involves a metal and a non-metal, or elements of high electronegativity difference. Yes, Emmanuel. Yes, look at this now. This is positive. This is negative. That's what we mean by polarity. When you get to hydrogen and chlorine, it is usually one will be partial positive, one will be partial negative. So the polarity is not always high because they didn't accept it totally. I will explain it better as we are moving on. You will understand it better when you get to covalent. But polarity simply means opposite poles, positive and negative. And you can only have positive and negative when there is complete transfer. You know, when this one transfer, it becomes positive. When this one accepts, it becomes negative. That means there is high polarity. Do you get that? So now, for the properties of ionic bonding, first thing is that this guy is positive, this guy is negative. And in physics, from the law of electrostatic attraction, it says that when the force of attraction between 2-point charges is directly proportional to the product of the charge and inversely proportional to the distance between them, abi, square of the distance between them. Now, there's a positive charge and there's a negative charge. What do you think will happen? So that means one of the properties that there will be high electrostatic force of attraction. So the first property you can think of is that there will be what? High electrostatic force of attraction. The positive and negative will link up and they will form bond. That is what we call electrostatic force. Then another thing is that it's going to be made up of aggregates of charges. Elizabeth Imujima lọ́jọ́ kan. For ionic bonding, it's going to be made up of, we are stopping by 20 and 11:20 and 12:20. 12:05, and we are stopping by 12:20. We started 10:30. So they will have their break till 1, then we'll complete the physics by, we are stopping 12:30. We are stopping 12:30. Then they will have their break from 12. they are said to have high boiling and melting points. So they have high melting and boiling points. So compounds that are joined together by electrostatic force of attraction, they usually have what we call high melting and boiling points. Is that taken? And you know they are made up of aggregates of charges. But when sodium and chlorine come together, they link up. And if you have been studying electricity, movement of charges will bring about electricity, abi? But now for sodium and chlorine, they don't move. They are together as solid. But when you put them in liquid, they are separated. We call it solvation. Now, at the end of the day, when they are in solution or molten, they conduct electricity. Marvelous. So when they are in solution or they are in their molten states, they conduct electricity because the ions are free to move about. And we apply that when we get to electrolysis. So in addition to that, what other property do they have? High polarity. There is high polarity. So let's move on. You can think about several examples you want to think about. Now, let me ask you this. They now give you this configuration and say that what is the combining power and what is the likely formula you have to have. This is how you will do it. Sodium has 1s2, or they just say element X has 1s2, 2s2, 2p6, 3s1, and element Y has 1s2, 2s2, 2p6, 3s2, 3p5. They now ask you, they give you this configuration and say that what is the formula that is formed by this guy? If you want to know the formula, first thing you will think about is one, their combining power. Their combining power. What is the combining power for this guy? 1, abi? Or you can say 1 or 7, abi? You know it can either accept 7 or lose 1. Shebi? Yes. For this one, what is the combining power? 7 or 1. Don't say 3 or 5, except you are not in the periodic table class, where I taught you that when you have 3, you will add these two together, abi? So now, this one is going to be 7 or 1. That means it will either lose 7 or gain 1. Will you prefer to gain 1 or lose 7? Gain 1. Will this one prefer to lose 1 or gain 7? Lose 1. I hope you are seeing. So that means that the combining power for this is going to be 1. Then for Y is also going to be 1. So what will be the formula? You will exchange it, XY. That's the formula. Are you following? Let me give you another analogy for that. Everybody. In some cases too, you might see two options that will be close to each other. So let's say I have X is 1s2. So can you tell what formula? So what will be the answer? Eh? The rain is rolling down. What do we have? What's the answer? Eh? Are you sure? Are you sure? What's the combining power for this? Eh? 3. You know it can either be 3 or 5. What's the combining power for this? So if you exchange them, this will be x3, y1. So when you exchange them, that's xy3. That's your answer. Do you get that point? This one is not about what type of bonds now. But if they now ask you that what type of bond exists here, you will look at it. X 2, 2, 3. That's 2, 5. That's a non-metal. This one is also like a non-metal, so it is not ionic. Since this one is non-metal, this one is also non-metal. It is not ionic. You will see now the next one is covalent. So the type of bond that will actually exist is covalent. So let's move on to the next type. Please, do we get everything about ionic now? Eh? So the next one is covalent. Quickly. So number 2, covalence. So when it involves covalent bonding, it usually involves non-metal and non-metal. Yes. So when you have a non-metal and a non-metal, then data is not. Shoshinlo, unlo. She unlo data. Wolo connect. So when you have a non-metal and a non-metal, every time you see a non-metal and a non-metal, I just give you that nitrogen and then oxygen. I say what type of bond will exist? Nitrogen is a non-metal, oxygen is a non-metal. Just know that is what? Covalent. Do you get that? I hope you are still following. Don't worry, I will stop soon. What is doing? When it involves sharing of electron, when it involves sharing, this one's involve transfer. When it involves sharing, and when you are sharing, there's a way it happens. When you are sharing electron, you use what we call Lewis dot method. And when you are using Lewis dot method, 2 electrons represent a bond. 2 electrons represent a bond when you are using Lewis dot method. And don't forget, most times, the electron donated or equal number of electrons can be shared. I'm not saying must be shared. Equal number of electrons can be shared. Let's take an example. They said nitrogen and hydrogen. You should form a bond between them. Nitrogen by Lewis dots. What you are going to do is it has 2, 5. So you represent just the valence electron because that's the one that will be used in bonding. You represent 1, 2, 3, 4, 5. That's for nitrogen. For hydrogen is 1. But now, this guy needs 3 electrons. If hydrogen donates 1, that's what I said. Equal number of electrons can be shared. If hydrogen gives this guy 1, this guy will give it 1 too. So this one cannot give 1, this one will now give 2. Meaning that this hydrogen must be up to 3. Because this one needs 3. So one hydrogen will come, share 1. Another hydrogen will come, share 1. And another hydrogen will come, share 1. When you count for this hydrogen, it is 2 already. When you count for this one too, it is 2. Count for this. So at the end of the day, this guy, the nitrogen, the lone pair of electron, and this. So that is called the Lewis dot method. So you put this nitrogen, put all the valence electron, which are 5, you put them. Then the elements you want to join, start pairing them up. This hydrogen has 1, so definitely it will also get 1. So this will donate 1, this also donates 1, and that's what we are seeing here. I hope you are following. This will donate 1, this will also donate 1. Please, as I'm talking, some of you are just busy talking. I could see you distracted, but I'm not talking. Anybody that come and meet you that teach me, please don't teach them. Yes, a lot of you like this. Instead of you to listen, you will not listen. The person that will teach you now, even if you don't understand fully, at least listen. When you now go and meet someone else, then the person will now explain, then you will now get it clearly. I might not be able to attend to all your problems now, but if you don't listen, you will still find it difficult, even if someone else is explaining. At least little by little, your man learn. As I'm saying it now, it might not be clear to you. It might. So nitrogen already completed 8, hydrogen completed 2, and at the end of the day, everything is balanced. Then we call that covalent bonding because they are now sharing, unlike the other one that they were donating. So these 2 electrons now represent a single bond. These 2 electrons represent a single bond. These 2 represent a single bond. In this molecule now, this guy is said to have 3 bond pairs and 1 lone pair. 3 bond pairs and 1 lone pair. So 1 lone pair means this one is not involved in bonding. These 3 are involved in bonding, so we call them bond pairs. I'm still going to talk about separate theory soon. So now, for covalent bonding, it usually involves elements of close electronegativity difference. Most times, elements that exhibit covalent bonding, their electronegativity is always close. Then they are going to have no or low polarity. That's why we have 2 types of covalent bonding. We have what we call polar covalent bonding and non-polar covalent bonding. And let me quickly explain that. Then we'll talk about the properties and we call it a class. Because I know some of you are tired. So now, when you're talking about types of covalent compounds, we have what we call non-polar covalent compound. And we have what we call polar covalent compounds. So they can ask you. Covalence simply means they will share electron. But those electrons they are sharing, is it equally shared or one gains more than the other? When it is equally shared, electrons are equally shared. Then you say that you have non-polar. When one electron not equal, so look at chlorine. Chlorine is 17 and the configuration is 2,8, 7. Abi, if I use Lewis dot method, it's going to be 1, 2, 3, 4, 5, 6, 7. Abi, how many electrons does it need? 1. Then I want to join it to another chlorine. Chlorine and chlorine coming together. Chlorine is non-metal. This one is also what? Non-metal. So the type of bond you expected to have is covalent. How are they going to do it? They are going to share their electron. How will they share it? I can use my Lewis dot and they will share their electron. So now this will also be 2, 8, 7. But now using Lewis dot, we have dot, 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 that. Right? This needs 1 electron. This also needs 1 electron. So what do? They will link up. And by the time they link up, they are going to form a bond. So this chlorine brings its own dot. The other chlorine brings its own cross. Then they pair up like that. At the end of the day, they will form a bond between them because they are sharing electron. Then you are going to have a bond. 2 electrons represent a single bond. The question now is that this bond that is between them, is it polar or non-polar? That's now the question. Electron, we talked about something. How to differentiate this guy is the electronegativity. Electronegativity is the tendency of an atom to pull electron towards itself. This is like a tug of